Hello everyone. I think we are live once more. As usual, I start my streams with a sip of something to drink. It looks beautiful on stream, I'm sure. It's like people eating on stream, which is usually not very charming. Okay, so this will be the 7th stream that I'm doing on Rust. And in the past 6 streams, we have been writing a epidemiological simulation. Initially, it was just more about understanding the Rust syntax, and then it became also about multi-threading this. So coming up with a paradigm for multi-threading this simulation ended up using channels and multiple simulation workers. And I don't know if I'm very happy with the solution, but it works. So we do indeed have a multi-threaded version of it. And basically, since the last stream, I ran out of time. But because of that, I will go through quickly today the output of that, the final version of that, which was also modularized. But then we'll do something interesting, and I think this is probably the cooler part of this stream. If it works, I have been poking a little bit at this thing before. But what I want to do is I want to take that simulation, or actually I want to take the non-multi-threaded version of that simulation, and I want to try and run that in a web browser. So previously that would have required a rewrite or a server architecture, in the sense that you would have to push something back and forth. So the browser would just be sort of like a thin client towards whatever was happening on the server. But what we're going to do today is one of the things that I think is very neat, and one of the new techs that I think should have huge potential for doing cool things online, and that is WebAssembly, or WASM. So we're gonna try to compile the simulation into WebAssembly. And we're gonna do that using the command line version of that. And then if everything goes well, I'll try to plot the output of the epidemiological simulation with a JavaScript library. So in order to do that, we will have to push some data from the Rust code into JavaScript, at least when it runs. So what I envision for this is that I want to have basically a small configuration panel where you in the web browser, where you set up how you want the simulation to run, like how many people will be in it, or for how many days. And then you click a button and it triggers the function in the WebAssembly code that will execute the simulation in your browser. So this is just very simple stuff. I'm just playing with this because I want to learn the language, and I still have so much to learn about Rust. And I also want to get this sort of interesting example up of WebAssembly. And then if we have time, and again, like before, I might have to split this stream into multiple parts, because the things that we're trying to do will take some time. And probably we're gonna hit snags, right? We're gonna bump into something, or we're gonna run out of time, or yeah. So probably there'll be more than one part this stream. But what I want to do finally there is I would like to set it up so that the code for the epidemiological simulation exists as a library, and then I would like to have a command line version of it that I can run from Linux or Windows or whatever target it's compiled to. And then I would like also for the same library to compile into a website. In fact, not to a website, but it should compile into WebAssembly. So it's precisely the same library could execute both in the browser and the command line. This is a bit magical, right? You can do something very similar in Kotlin, because Kotlin has multi-platform targets, so it can compile Kotlin into not just WebAssembly, it can actually compile Kotlin into JavaScript, which is super neat. But what I'm going for here is, I think if WebAssembly works well, then there are clear benefits to that as well, because compiling, say, Kotlin to JavaScript, you're going to have the speed characteristics of and execution characteristics of JavaScript. But if you compile it to WebAssembly, you should in principle have very high performance. At least this is how I understand it. Like the way that executes is really fast. I'm also curious to see the size of the executables, the WebAssembly executables that can be delivered by Rust. So just to briefly go through what we're talking about here. So we've written a simulation. This is the output of the simulation, and it simulates an epidemiological outbreak of some unspecified pathogen. So it basically just counts 300 days. In this particular output that we have here, it counted 100 days. It had 10,000 people in the simulation, as you can see here, and then this is how many people recover from the disease, which is just lagging a little bit behind, a few days behind how many people actively had the disease. And then you have this list here as well of active infections. So what we're looking at is it's basic, very basic model where you have a large list of people, and as people get the infection, they will infect others over the course of several days. And then you get, once you've had the condition, you can no longer be sick or get reinfected. Since nobody dies in our simulation, we get something like this, which shows this rapid rise in infections that start off slow and explodes like they experienced in Italy with COVID. And then it plateaus and falls out here. So this assumes no interventions in the development of the disease. So it just runs. It's like I said, it's sort of a toy simulation. It's very simple. It doesn't. It's not supposed to be academic or hard science in any way. This is just purely to learn Rust and Rust programming. Okay, so so let's get to business. First, I will have, like I promised, I will have a brief look at the multi-threaded version of the simulation that I didn't manage to finish in the last stream. I'll just briefly go through that. If you're not interested in that and just interested in the WebAssembly part, and you're watching this on YouTube afterwards, check down in the comments. I'll put a time marker for the part where we get to the WebAssembly compilation and exploring that. Just gotta say one more time, these streams this is my learning curve that you're watching here. I'm not a Rust programmer. I'm not a professional programmer, but I do program for work for a variety of reasons, and I do enjoy programming languages, and that's one of the reasons I'm exploring Rust now. So this will be hampered by my incompetence with the language, but that's also what I'm trying to do here. I'm trying to climb the learning curve, and perhaps someone can learn something by watching these streams. Okay, so let's open CLion, which is the IDE I've been using. I've been very pleased with it. There's an update to it now, so now I think it's better on Windows as well. It had some debugging issues. You couldn't see into arrays and so on Windows if you put the breakpoint down. But it has apparently gotten better there, so maybe it's now viable to debug on Windows as well. Okay, so first we're going to open the final version of the simulation. Okay, so we tried. Okay, so the simulation consists in memory of one large array of people. At least that was the initial version. And then as all these people are referenced to by their index in this array, which is, of course, you don't have to look anything up. You can just pop to the index. So this is a fast way of looking up stuff. And then each of these people have a sickness state. Whether they are susceptible to infection, whether they are sick at the moment, infected, or whether they have recovered. And then when they are infected, as the simulation ticks day by day, then they infect other people, and by picking a random index, so there's no clustering or there's no graph structure of the infected people here. And then they try to infect that individual, and if that person is susceptible, then they start the clinical course, and then so it goes, and they infect others, and so on. And that's how you get the characteristics of this exponential growth until immunity sets in. Okay, so the challenge for the multitasking, as we explored in the last couple of streams, has been the fact that all of these people are in one huge array. So you cannot in Rust just pass this array to multiple threads. You cannot do that anywhere really, because you will have read and write issues with it. There are perhaps architectural things in this particular implementation that we're looking at here with one large array that you know the size of, that perhaps you could do some of these things without thinking about the mutex and locking it, because it will be the same size in memory all the time, no matter how much the threads work on it. You will not really mutate this array because it is an unmutable array, but the elements in the array are mutable. So with the borrow checker limitations, we cannot simply pass. We cannot easily, or we can easily, but it's not pretty to pass the array into multiple threads, then you have to use these memory management APIs that Rust provides for situations where the borrow checker is not sufficient, and these are the arc, the archetype, the rvlock, and so on. So I tried to put rvlock on the array, and that really didn't increase the speed of the simulation very much. Then I tried to put an rvlock on each individual person. That slowed down the simulation significantly. So what I ended up trying to do here in the end was to try to split the array. Okay, so here's what it does. It takes that huge array, but instead of creating one big one of people that are in a simulation, it creates it in chunks. So it splits the simulation into multiple sim workers, and each of these get a chunk of the array. And then if there's an infection that infects someone that's not in their array, they send a message to the sim worker that has the chunk of the array where that person is, and then this is how the simulation runs. So this turned out to be a little bit complicated. So we can go through the simulation now. I modularized it. So let's just briefly go through the code. I don't want to spend too much time on this, but we do have to have a little look at it since we started it. Okay, so let's see what happens here. So in the main, so right now it takes arguments from the command line to just say how many people are in the simulation and the number of threads. And then it passes that into the simulation object, so it creates a sim new. Then for up to 300 days, it takes. You should probably have a command line argument here to say how many days as well, right? So it takes through the simulation, so 300 times in this particular case, which is hard-coded in. It takes sim.nextDay, and then it goes sim_finish, which collects the data from the threads, closes the threads, and collects the data. And then finally, we output a CSV file, which contains the output from the simulation, where you can read out the numbers and do your plots and analysis on the characteristics of this infection. So if we go into simulation, we can see what it does. So before simulation was an object that contained a large area of people. Now it's an object that contains a vector of join handles, and that is effectively a reference to the threads that it creates. It contains some objects that describe the workers in the vector. It also has a channel, the receiver end of a multi-producer single consumer channel, and this is how all the communication between the threads happen. So it has a receiver called ready receiver, and then each of the threads get a send channel where they can put anything. They can put a boolean into this, and so because the thing that happens is that, okay, so you are the simulation, you are the sim workers, and let's say that we have created 8 sim workers, and each of you have a chunk of the array of people that are being simulated. So each of you sit on a certain range of people that are in your simulation. Then first of all, you gotta have a message. You gotta be able to tell the simulation worker that now we want you to tick to the next day. So now it's day 10 of the simulation. So you ask it to say, do the next day, and then it calculates. Each worker will calculate the infections for day 10. But then they will end up with a list of the ones that are infected, that are not of the new people to infect, that are not in their own chunk of people that they have account for. They have to pass that to the thread that has those people. And in order to do that, so here's the question: what happens if that other thread comes to the point in its execution where it processes and infects those people, and then it finishes? So the challenge here is that you have, at least as I imagine it, you have to have synchronization points. So it becomes less fluid and multi-threaded, and more several workers with synchronization points. And that means that every now and then some of these workers are going to wait for the other workers. So that becomes a challenge. You have to synchronize. So we have the ready receiver, which basically, whenever a thread finishes a step in its simulation, such as we've now found all infected, and then next it will go through and infect the people that now needs to be infected, and finally it needs to say that it's done. And initially it also needs to have a way to tell the simulation that the thread is ready. It has initialized all the people in the array of people that each worker has. so that it is now ready to go. So it has to send a message back to the controlling entity, which is the simulation, about we're done with this day, we're done in initializing, we're done infecting new people. So for that we have a ready receiver, and what the simulation will do is just whenever it tells the threads to do anything, it will just sit and wait for this channel, and it will count, it will loop for as many rounds as there are workers, and then it will basically, at the point where it comes to that point, it has counted up as many messages in this channel as there are workers, then it knows that all the workers are ready, and that's how this channel receiver works. Okay, so there's also so what goes into the channels? In this case, it's the ready receiver. We can have look at the simulation. So here's how it ended up. So I have this module here with the person, the sim worker, and the actual module. The module contains the simulation itself. So the simulation, when it's new, just spawns a bunch of workers. It collects information about those workers, and in each of these worker infos objects, which we'll have a look at in a moment, there is a channel that can be used to communicate with that worker. This array of this vector of sim worker info is actually shared with all the threads so that they can look up what other thread to communicate to. And it does that using one of these memory management APIs, because here you have an object that needs to be shared with multiple other objects, right? So we do put that in an arc, I believe. Let's see if we do that down here. Oh, this was a long function. Should probably have split this into a couple of more. I think so sim worker infos is this. What is sim worker infos? The vector. Yeah, actually, oh no, I understood. Now I remember what I do here. Yeah, so instead of putting it in an arc, which I could have done, it actually clones this object because it is static, it doesn't change. And you can clone every element of the worker info. You can clone, so it doesn't contain the join handle, that could probably not be cloned. But you can clone the sender channels. You can have as many of those as you want. I assume they have some internal reference counting. Because you so that the channel is open until all the senders drop out of memory, for instance. Because you can clone them, and that's what happens here. It clones the worker info and passes that array of worker infos into the newly created workers. Okay, so that's what it does. It spawns lots of sim worker objects. We'll have a look at that in a moment. And then it collects information about those and keeps a copy for itself, and every single sim worker also gets a copy of the list of other workers, so they can look up what channel to send information about new infected people to. For instance, I'll just get an example to explain that. So let's say you are worker number 3 and you have person 1000 to 2000. Then person 3000 needs to get an infection. Then you have to look up in this sim worker info array what thread has that, and then you put the number of, so each sim worker info has a channel that you can put an ID into of the people you want to infect. So you will look through the sim worker vector, the array, and then you'll find the worker that has that covers ID 3000, and then you'll take the channel to that thread, and you'll put well, I would like you to infect number 3000, so you put that number into the channel, and there you go. Okay, so basically this is how simulation sets up the sim workers, which actually perform the simulation itself. And here's a function that ensures, okay, so once you've created all these workers and you're just letting them go, here, do your work, initialize your stuff, and so on, you gotta know that they're ready to receive further messages and perform the simulation before you start on day number 1. So in order to do that, I have a function here called await ready workers. And like I said, what it does, it simply loops through. I'm going to make this a little bit bigger. So this function simply loops through all the worker handles. Yeah, so the join handles basically contain a reference to each of these threads. So it will loop through those. So you know how many there are. And then it will ask for a message from the receiver for that. Okay, so all the threads put messages to the same receiver, meaning that if you have 10 threads, you can call this blocking function 10 times. What it does is that it just ticks up 10 iterations here. where it does this. And at the point where all the workers have checked in, you know that you're ready to go. You could do error handling here, because if one of these senders panic, then you can do error management here and check that, okay, because you cannot wait. This would be a never finishing loop if you did not do error handling here. So if one of them crashes right now, the entire system panics. But you could of course deal with this situation where one of the senders goes out of scope, crashes for whatever reason, and there's a panic in the system. Okay, the final method that we can think about here, I'm just going to go through this real quick now, is the next day one. And it has two steps. First, it tells all the workers to process the next day. So it loops through the workers and it sends them this thread control message for next day. Basically what that means is that this is one of those beautiful Rust enums where you can put data inside the enum. So it just sends it the next day enum and what day it is. So this will be day 1, 2, 3, 4 up to say 300 if you're simulating 300 days. And then once it's done this, it awaits ready workers, this function up here, just to see that they have all completed the task. And notice how we send this message for the workers to process the next day. We send through another channel called control sender. And control sender, as you may be able to see in the hint here, is a sender for thread control. So then we wait for synchronization to occur. So all of them have checked in that they're ready with their task. Then we do the same thing for handle infections, because now all of them have a list in their infection reception channel that says these are the ones that you are responsible for infecting. And then it comes to that point, and then it loops through that, each of these sim workers, and loops through that. And again, we do await ready workers. And once we know that's done, we're done with that day of the simulation. So we do next day, handle infections, and for each of those we have to synchronize. Of course, maybe we're losing some time if one of them is for whatever reason, maybe scheduling things in the OS or whatever, I don't know. Maybe if one of them are stopping for a bit, then of course all the other ones have to wait. So this is probably not the best possible way to perform this simulation. Although it is hard, because in some ways all these sim workers and all the threads have to operate on the same day. I'm sure there are ways you can implement this simulation that would sort of span out asynchronously, and that would be a neat way to implement a simulation like this. You could probably tick up, like, for each individual, the days that they have managed or been managed, or how far along the simulation each individual person is. Then maybe you could do a massive asynchronous way to perform this simulation. That would be a cool thing to explore, but I feel a little bit done with this simulation stuff now, so I'm not going to do that. Okay, so at finish, we basically just we take the join handles that we have, and then we loop through them, and we just join. We send them a signal. Again, we use the workers control sender channel, and we send thread control done in them. Don't pass any data there. We just tell them that we're done, and then they all have responsibility to exit. And then we join all those join handles, and there we are. Then we collect the data. Yeah, I don't think I'm going to go through the person array. Basically, it has each person has a state, like I said, and a sick course, how they progress through the disease. And in a proper simulation, you probably would like to have some variability on how they progress and how many people they infect and so on. And if you wanted to have interventions, like you wanted to implement social distancing, then probably you would like to have a graph of people and how they are connected. And then you may want to alter the graph and see the effect that you would have on the spread of the pathogen. These are really these are cool simulations, right? You can simulate all kinds of interesting things. The only observation that I made in this simple simulation is that not everyone gets infected. That is like a very, very small, I guess. My OpenOffice has this funky thing where it creates this teeny tiny window sometimes. Because the one thing that I observed that I was not sort of expecting from this simulation, but that is sort of obvious when you think about it, is that you do have a certain number of people that the infection never reaches them by chance, and by the time they would get infected, so many people are immune that the infection could never reach them. So there is like a lucky few up here. It ends up being around 5%, I think, of the people in all the versions of the simulation that just don't get the disease because they were lucky. Okay, so the simulation workers, I don't think we need to dig too much into that, but again, they have these control sender and infection sender. This is actually the sim worker info, the one I was talking about before. This is the structure that we clone and send to all the sim workers, a vector of that key, so that all the sim workers know about all the other sim workers. One way you could have done this, if you didn't want to clone the object, is to put it inside some kind of reference counter, such as arc, which is the API to create an asynchronous reference counter, and then you are, instead of doing the sort of safe approach to memory management that Rust does at compile time, you're doing some parts of that work at runtime by effectively creating a garbage collector. When there are no more references to this array, it will to this array. If it was inside of a arc, it would just drop at the point where there were no further references, because then it could never be accessed, right? Okay, so sim workers, I don't think I'm going to go through this, but it does provide these list of these interesting channels that they needed. So they had to have a receiver to get control messages, like we said in simulation. You have to be able to tell them that, okay, go for the next day, go to deal with the infections, and now you want to finish up. Then they had to have a channel where they would receive all the IDs of the people that they were responsible for infecting. So they have a receiver for that, and then they have a ready sender, which is that. You remember in the sim object we had all these. We had one receiver that we ticked up as we looped through and waited for signal in that receiver until the point where we had done that as many times as there were simulation workers, and that this is the sender objects, plural, that gets put into the sim worker. Yeah, I don't think I'm going to go through how the simulation works. If you want to know how it actually works and how it deals with infections, you can go back and check one of the previous streams. I think the most interesting part about this has been the experience of creating something multi-threaded in Rust. And to be honest, I have never felt more safe with my multi-threaded code than I have been writing this simulation. Because it seems like, you cannot make a mistake. That's not true. You can probably do so many mistakes. But it feels like at least the things that have to do with managing where the resources are and so on is that Rust delivers. Like it promises you to have fearless concurrency. Like that's the sort of what do you want to call the not a jingle. This is like this sales pitch, the thing that you're trying to sell with the multi-threading here, and it really feels from this initial experience with Rust. It feels like it has some merit. It feels like that. It feels like the fact that you cannot these limitation that Rust puts on your pointers. That's basically what it is. Not limitations, but the rules that it applies to managing pointers and where they can be and who you can share them with and who is allowed to change data in pointers and pointers. It feels like it was so perfectly made for multi-threading. Apparently, from what I hear, this was not actually the goal of the project, but it sort of landed there that this approach really works for multi-threading too. So writing this simulation, I felt safer than I've ever done writing any kind of code like this, and that is itself a beautiful experience. That's not to say that Rust doesn't have complexities. We will, I think, next set of streams I will make after I'm completing the WebAssembly one is a series where I will look at some a more complex data structure that I have made before, and that is event-driven programming, and how does this fit in? Sorry, how does this fit into Rust, if at all? And I think that's going to be a tricky one, because I think I would like to first and foremost try to find an alternative, and I think I've found a good one. I want to make a stream about that. But I also would really like to try to see how you could implement event-driven programming. And the problem here is who owns the objects that are triggered by the events. So you cannot, like what I would do in TypeScript or C#, for instance, is that I would put a closure on the event handler or something like this, and then I would put the self or this into that closure, and then you cannot do that in Rust, because then you're moving self into the closure. So if you wanted multiple closures for event handling, then you would have to move multiple those self objects into event handlers, and you cannot do that, right? Or you can, but then you need to have locking structures and so on. Maybe that will be the answer, actually. So, WebAssembly. If you don't know, WebAssembly is bytecode for the web. Okay, so, or machine code for the web. So, modern browsers have a runtime for WebAssembly in them, and basically it allows you to, instead of creating dynamic code with JavaScript or Flash to some plugin, you can compile yourself an executable and put that in the browser and have that run. That's it. Easy and hard. The first thing is obviously that, so if you wanted to make like a multi-platform project that could execute both in browsers and in the command line, or on like a proper piece of hardware or a proper piece of OS, then you will of course have a bunch of resources that you will need to abstract to be able to have that executable running both. And apparently there is a project that does some of this for Rust already, so you can compile programs and expect compatibility because it has like abstractions for many of the things you want, such as random number generators and OS file access and things like this. So of course, if you have such an abstraction layer, you can really compile any program, or there are a lot of programs, and put them in the browser like that and execute them. But what I'm most curious about is how I can make a library that I can take where I can run functions from that library and have those functions interact with JavaScript. I'm not sure I want that compatibility layer, at least not initially. I would like just to have a simple executable running on WebAssembly that I can call functions on. So what we're going to do today is we're going to take the non-multi-threaded version of our simulation, which we created here, I think in stream 3. I think that's the one we're going to pick out. And then we're going to try to adapt that one. The reason I'm not taking the one with the multi-threading is quite simply because that one has spawning threads, and you cannot have multi-threaded code running, at least not without some kind of compatibility or abstractions. You cannot have multi-threaded code running in the browser in WebAssembly. So I'm gonna take a simpler version which is not threaded, and then we're gonna use this thing called wasm-bindgen, and we're gonna generate for bindings that you can call from JavaScript. Yeah, so I think let's just get to it. So the goal again is we're going to create a web page. It's going to have a box that has a number in it, where you can add how many people you want to put in your simulation. You click the box, simulation runs, you get a graph. At least initially, perhaps just a number, but at least you get a graph at the end that shows how the simulation developed, right? And then I want this to compile as a library eventually, both for the command line and for the browser. Let's just start by getting it to run. So now we're going to create a new set of projects. So what I'm going to do is I'm going to just copy the data from the third stream into this one, but let's just create a new workspace. So cargo new wasm.model. Okay, so we have our package and we are off. Let's inform CLion that this is the one we want to work on. And here we are. Now we don't have a lot of things here. New project, so it's asking for kinds of things here. Now what I want to do is I want to copy the simulation into this folder that we've just created. Let's pop up a couple of these file managers. Okay, so we have our projects, and then we have our wasm. Then we're going to go the same here, and then I want to copy from the third stream. We take the simulation object, we can copy that. I'm going to drop it here. And and we now have our simulation module here. I think this is a module, isn't it? And we're actually gonna get rid of a couple of these things because we need to simplify it. So we want the printing to be gone, and there's a snag with generating random numbers. So we need to modify one of the packages that we depend on to generate random numbers. So actually, Rust standard library doesn't come with a random number generator, but it has a package called rand, which appears to be the thing everyone uses. Rand also happens to be famous author and the currency, South Africa, I learned. So TIL, today I learned. So let's use mod simulation. Side point. Interesting how Rust deals with modules. Because I thought maybe I don't get it, maybe I do, I don't know. But it appears that modules, if I was writing JavaScript, I would write multiple files, and then one file would call the other files. And then, yes, it does get included, but you would sort of have dependencies between the files. It appears Rust does something similar, but it's more about including. So it seems like if my main includes multiple files, then I can still get code completion without and even though some of those files depend on each other, they don't have to have this statement here. So for instance, if I had a sim worker thing here and simulation depended on sim worker, then simulation would not have to ask for sim worker as long as the main contained both mod sim and mod sim worker. So it's like it doesn't actually look at each individual file and what that file includes. It looks at what the entire project includes, or the target that you're trying to compile, what that includes. That's how I understand it, because it seemed a bit counterintuitive. Because I expected that in the channel example, in the multi-threaded version, that I would have to have every single file importing the things that it needed, but that was not true. It needed to have the main. Or in one of these cases, sorry, the neighbor's drilling here. In one of these cases, it needed to have the actual main module include everything, and then even though the individual files didn't have these inclusions, it still worked. So the way it includes is a bit different from what I expect from other languages. Okay, we included the simulation. We're actually going to trim this down. We're going to remove pretty table. We're going to keep rand for now, and I'm going to show you why it doesn't work. Okay, let's up the size a little bit here, make things a little bit more manageable for small screens. Okay, so what we got from pretty table was this table element here. Oh, I do hope the neighbor doesn't drill too much today, otherwise it's a bad time. He's building himself quite a little garden in his apartment, or outside of it actually. Okay, so we remove table, and then at the end here we add, let's see, each day we add a row to this table that includes how many, what day it is, how many susceptible, how many infected you had that day, and how many have recovered. So we want to remove these parts. We still want to count them because we do want to log them. So we'll add a little to do, add logging here. Can I see this and see a line down here? Yeah, I do. Look at that. Add logging. I hope, I'm not sure if you can hear it. In some ways I hope you do, in some ways I don't. But usually he plays music, but I think that he's drilling. Okay, so now we should have our simulation out. We can go to main, and then now we should be able to instance our simulation. So we'll create a new simulation. We'll call it, actually we're going to just see if this compiles. So we're going to compile main. Okay, end result import rand. Of course, we have to go into our dependencies and declare it. We're going to do this first the wrong way, and then we're going to do it the right way afterwards. Why am I not getting the rand crate? Well, actually, these crates are really well documented, so I can just go rust rand crate. Actually, I've been searching for some other things here. So in the package registry, we find the crate called rand this one, so we will just include that. This is what we need, and it's 0.3. We can include that since that's what we 0.3. Okay, does it compile now? Yeah. Actually put this compiler thing out on the side here. We got some warnings about things that are never used. I should probably turn off the dead code flag. Okay, so now we have added this dependency, and in a moment we'll see why this is not enough. Okay, so we now have our infection here. We can get build. And then now, so it will output at the end a table file. But it will, right now it doesn't actually log anything, but we can try to run it and see what happens. Now it just says hello world. We're actually not creating a simulation. We can just try to create a simulation, see that it works. So in main, we're going to do let sim, will be immutable sim equals simulation new. And then, yeah, it was just how many people were in it. We had 10,000 people now, and then sim, we can just do 1 day. So it's day 1. And I don't think it had like a finish thing in this version. Just do this. Yeah, that works. Doesn't crash. Great. All right, so there we are. Okay, so what we want to do now is we want to compile this into WebAssembly. That's basically what we want to do. But if we just make a WebAssembly, we have no way of accessing the internals, right? We have no way of getting stuff. We have no way of telling it, as far as I understand, what we want. It's just a box that sits there. You can tell it where to start the WebAssembly, apparently. But we are going to create a function called runsim. It has to be a public function, runsim. And we will export this function to JavaScript. And that will do exactly what this did. For now, we will just add, we'll have it simulate a million people, and we're going to simulate them for 300 days. And the reason is that I want it to take a little bit of time. So we're going to do for day in 0.300, and then we come down here, the day in. What happens if we run? Okay, so we'll call runsim from here. I think at the final, okay, so right now the sim doesn't actually output anything, so we need to capture the output. But let's just run this and see what happens. So it takes a few seconds, right? Oh, we should probably tell when it's done. I don't remember how long it took for 1 million people. It takes longer in debug than release, but the ones we're done, we're actually going to have it print line done. We can put that in the, we can leave it there. Yeah. It's still running. Maybe that was a little bit heavy. For an optimized executable, we're going to put 100,000 people. Let's try that. And it's done. Okay, so there was a little bit, it took a little bit of time. Okay. So next thing we're going to do now is we are going to take this and then we're going to create this into WebAssembly. And I think we could just compile this now into WebAssembly. But we need a way to access this function, and that's not going to happen if you just compile it. But I think we can just compile it. Okay, so now we are in our directory. We have our stuff. So we are now going to transform this into a website. So we're going to make a directory called web. And now we're going to use, first we're going to use cargo. We're going to build it, but we're going to build it for another target than the one that's default. We're going to build it for wasm-32 unknown. So there is another target you can build it for, which will create that sort of compatibility, and that is wasm-32 unknown mscripten. And that one, I haven't dug into that yet because I'm curious, first of all, about this using it like a library rather than a full application. So, but it might be that is a better way than what I'm doing right now. Okay, let's compile. So it did compile, and if we have a look here now, we will see if we Let's look in the file browser. If you go into I do prefer command. Now we have the inside debug here. You can we have the model inside the regular target debug. We have the one we compiled before, but we now have a new target here that also has its own debug, and it's interesting to see what came out of it here. So we do have a wasm file here now. This is the file that will serve to the browser, but it's 3 megabytes. That is surprisingly big, I gotta say. I was not expecting that. Let's try to compile it for that target, but adding it to release so it optimizes. 100 and now, okay, 1.8 megabytes. It's actually quite chunky. I am surprised at how big this one ended up. That surprises me. That really surprises me. I wonder if it's because of the libraries that we're now compiling into it that makes it so large. But that is a surprise to me. I actually expected this to be much smaller. Let's make an experiment. Let's not depend on rand. In simulation, we're now going to create so we're going to create ourselves a function called getRandom. So we're going to create a public function called getRandom f32. It will give us a floating point, 32 bits, and then we will just have to turn numbers as 0 point. Yeah. And then we're gonna, instead of using rand, we're gonna just comment that out. We are going to use rand. Wrong language. We are going to use rand, but we're going to use it inside this function anyway. Okay, so let's, we have one called pick random index, and that's the one where we want to, I might actually have forgotten to seed the infection with infected people on this one. But yeah, we have to get back to that because I cannot remember if we did that manually in main on the third version of this. But yeah, it's fine. Okay, so we use this function called random to get that. So we're going to use getRandom f32 instead. Expected f64. Well, we can cast that, can't we, since it's less precision? Yeah. Okay, so I think actually if you run it now, does it run? Yeah, it runs. What I actually think happens now is that it hasn't seeded any infected people in the infection. So even though it takes a while to loop through everything, what you're seeing is just pure looping. It's not creating any infections. Okay, fine. So we have now replaced this brand here. Interesting how we got that now, because I already, yeah, of course. I think, do we have to put crate for here when we use this? Okay, let's just, okay, let's try and run it. Yeah, that's fine. Let's now see when we do this. I still have the dependency in the TOML file, but I'm just curious to see if we get a smaller executable now. Okay, so we're gonna build, optimize for release, the same thing. Let's build quickly. How big is the wasm now? Really, it's still 1.8 megabytes. What if we remove the dependency? Because now we don't need rand anymore. Can we still build it? Yep. Good, and then we compile. So our wasm file is still 1.8 megabyte. That is really surprising to me. I was not expecting that at all. The reason I was not expecting that is because people say that these are tiny executables, right? That really surprises me. Does it compile in a lot of things? Not sure. Okay, let's continue with our explorations, and we will try to get to the bottom of this. We'll also try to see what happens now when we do the bindings, and that's the next thing that we're going to do. Okay, so beyond the disappointment of the size of the executable, which is actually something, although I do hear that executables of this kind in Go is regularly 5 to 10 megabytes. But of course, we want this to be an efficient bytecode thing, right? So that one's a bit dodgy, that one. But yeah, let's get back to that later on. See if we can minimize it. There was a chapter about that in the WebAssembly book for Rust. So maybe there is some tricks there to make it smaller. Okay. What we need to do now is we want to be able to call this run sim from JavaScript, because the way that we will trigger anything in this WebAssembly, at least for now, is through JavaScript. So what we got to do is we got to add a library called wasm-bindgen, WebAssembly binding generator. Apparently, this is an officially supported library, so it's not like just something written by someone. So we're gonna add wasm-bindgen. There we are. And then in our main, we are going to use that. We're going to take external create wasm-bindgen. And when we do this, we can just compile it with that so we get all the stuff in. So when we do this, we get an attribute that you can put on functions and data structures that will create bindings for those things in a JavaScript file that you'll load. And then that JavaScript file loads the WebAssembly, and you can interact with the WebAssembly that way. And this did work quite well. Okay, so let's try this. Do I remember the syntax? Is it hash? Then it's this, and then it's wasm-bindgen. That doesn't look right. Is an exclamation mark here? No, that is definitely not. Well, is a bang? Okay, let's try. There's yeah, it is this. It is that thing. Underscore. Okay, underscore. Yeah, of course. That was my problem. So we have a thing here because when I looked up the wasm-bindgen documentation, it provided an example where you would use Node to create the web server, and it would pack it as well using a bundler. If you don't know web development, a bundler takes lots of stuff and puts it into a file and delivers like a JavaScript thing. So if you have multiple modules in your JavaScript thing, you can bundle it together. But what I want to do is I want to be able to understand what happens and see like what it looks like because I'm trying to understand the technology. I wanted to do this also not depend on Node. Depending on Node is just one of many scenarios for this. So I do like the idea of not using Node or a bundler. So we're just going to do this from the command line, which is nice anyway. The command line is lovely. Okay, so we added this attribute. Does it still compile? Cannot find attribute wasm-bindgen. Yeah, probably because we have to use wasm-bindgen, right? So okay, so we have included these two things, and we'll use wasm-bindgen. And it has a prelude like so many other Rust libraries. So we'll just include all of that. It runs. Does it actually run? It runs. So okay, so we can, even though we have tagged lots of this stuff with the wasm-bindgen thing, we can still run it on the command line, and that's important information. Because it means I think that we can now both create this library for the command line and for JavaScript. So what did we actually change by adding this attribute? I guess we added some information that we can now use to create the bindings. To create the bindings, we have a command line tool called wasm-bindgen, right? What we're going to do is we are going to target the web. And we are going to output this to what did we call it? We called it web, didn't we? So we can just output it to that. We can output it to web/package, and then we have to tell it where the thing is. So with the thing that we compile this. So we go to target wasm, then it's we can use the debug version. I guess we get more data from that, and then we do wasm epimodel.wasm, which is the file that it compiles. Okay, so unknown flag output did. I think it's called out did maybe. Okay, so that works. So I just remembered we do have to recompile. We're gonna do the debug version. So okay, so we do have to recompile it because we changed it. Okay, so if we now run it, it's really fast. Really fast. This is probably written in Rust. Okay, so what the question now becomes, what did it make? Let's list what's inside web. Okay, so that there's nothing there except the package thing that we specify as the output directory, and boom. Here's magic. We have a JavaScript module. We have TypeScript definitions. So if you are a TypeScript programmer, you'll know that this is pure. This is beautiful, right? Because then you can now get code completion, syntax highlighting, telesense, everything. You can just get that by importing, referencing this file. And then TypeScript, if you don't know, to me it's JavaScript with strong typing and some other features. And once you do TypeScript, you'll never do JavaScript again. It compiles to JavaScript, but it checks for errors first using the strong scripting, no strong typing. Okay, so, and we have the WebAssembly that we outputted. Has it done anything to it here? And then we do have the not actually sure what this one is. Is this a TypeScript file? Is this the same as this? It's like pure, but let's have a look at this one. So let's folder, and we go into projects and wasm epimodel, and okay, let's just open this whole shebang. So we can have a look at this one. It's okay, so this is the TypeScript definition. So now we can actually see what it exports for us. Because it has init function, and it has this is the function we're interested in. Remember, we created this function in our Rust code, the one called runsim. We know now that that function exists because it is in this TypeScript definition. What is these definition? Because this is actually really interesting. It seems like these TypeScript definitions Why do we have two? Is this like if you directly access the WebAssembly? Maybe using these, you can just load it up and directly access these functions. I don't know. Or is this like yeah, I'm not actually sure what this one. They seem to contain much of the same, but they are also quite different, right? Because these things were yeah. Okay, that's fine. Let's have a look at our, well, the wasm is a binary file, so we can't really look at that one. We can look at the JavaScript. We do here have a variable called wasm, yeah, and then we have a function. This module exports a function called runsim, which is the one that we put the wasm-bindgen. So remember, we put this wasm-bindgen thing here on runsim. Now we, using this command that we just, the wasm-bindgen command, we now get this module that you can load in. And it contains code here to boot in to load in the WebAssembly for us. So we will now, so the next thing that we need to do is we need to create ourselves an index file to load this. We get like a web page here. So we take that and we create a HTML file. We're going to call it index.html. And for now, I'm just going to copy from the example. It's actually very, very simple what this example code does. The example HTML file to load one of these JavaScript packages, or modules, sorry. This one contains a lot of information, but you can just directly see what it does. So the example is not actually what we call it. We called it package. Then we called it wasm-model.js. Okay, so interesting, right? So now we are basically in this inline module JavaScript here. We're importing this module. Then we are taking some functions on the import. We're taking init, and then we're going to do run sim. Now we get code completion. Lovely. And then we have a function here called run, which calls init, and this is some example code. We can take that away. Okay, so it has an async function init, so that's called run, and it awaits the completion of init. So again, let's have a look at init. I didn't find that, but it is in that module, and we can have a brief look at what it does. Package wasm-bindgen is the module. Let's see what init does. Okay, so it takes the name of the package. We defined that already here, and we told it. No, we don't actually put anything into it, but maybe it looks. Okay, so it will. Maybe it searches for this module. Sure. Anyway, somehow it finds the wasm file and then fetches. Yeah, it does fetch of that one. Then it awaits load of this and ports. What does ports do? An empty object. So what does load do? We can see that. This is the thing that actually loads it up for us. It right? It has to be the right MIME type. Then it calls WebAssembly instantiate, and then on ports. And then wasm.instance.export. Okay, so it seems like exports on this WebAssembly, on this whatever this WebAssembly thing returns. This is a WebAssembly instantiated source. Say that here too? No, it doesn't know what that is. And that is then, it has an exports field. Is something we set, or does it come with the WebAssembly? Yeah, and then it puts that into the wasm thing, and it calls, so it calls a function that's apparently specific to wasm-bindgen, and then it returns this object, and it exports the init function, and it does export the function here. Yeah, so it keeps this one, and then it exports. So basically, the JavaScript function we get here that's called run sim seems to just wrap this wasm.runSim function. So the WebAssembly seems to contain the exporters of functions that we can call. I guess we got this from the wasm-bindgen code, right? It created this JavaScript file for us. Now we should be able to load this up in a web browser. We don't have any outputs now, but we will know that if you call this function, it will take a little while for it to complete. We'll use that as an indication that things are going according to plan. So we will need to do the infamous Python instant web server. So we're going to do Python HTTP server. Yeah. Got the CGI though, but this is like the command to boot up a very small and quick web server. We're going to remove this CGI. Let's put it on port 8080. Yeah, Python 3. And serving on 88. Let's open localhost 80. Put up the debugging stuff here. Localhost 8080. I'm in the wrong directory. Yeah. No? Yeah, I gotta go into web. And this is where our index file is. Yes, this is index HTML and package is now in here. So let's pop the server up again and reload. Okay, so Nothing happened. Is that a good thing? Yeah, I guess it's a good thing. Did we get our WASM thing? Yeah, we did. 150 kilobytes of WASM was delivered to us. It did. It really shrunk down that assembly, didn't it? Now we're talking, right? 150 kilobytes for an epidemiology simulation delivered in our browser. I can live with that. The only question is, how do we call how? But of course, this does nothing, right? It doesn't have any. It doesn't do anything. What I want to do is I want to first of all, we can just try. We don't have the runs. Yeah, we do actually have runsim exported to the global scope. I thought we had to. Actually, thought we had to. I thought that we had to export this to the global scope manually, but apparently it's already here. So we can do. Can we do this? Runsim is not defined. Right, so it's not. It is not automatically exported. So what I'll do is that I will actually here after run I will do window runsim equals runsim. I think also disable cache. Important. We are just doing stuff. Disabled. Now we should have runsim. No. Didn't it reload? Oh, what's happening here? Did I run it by accident? Is that what's happening? Did we manage to crash Chrome out? No, so it is delivering the wasm file here. That was weird. It takes like ages to load. Because of that little change that I did there. I remove that again. Okay, something is not. Oh, no, look at that. So now, really surprised at the slow speed. Chrome is being a bit slow here, I guess. Is it the page? No. Let's try it one more time. Sorry, 80. I don't actually know why Chrome is being so slow here. Let's open it. Or is it this web server here somehow that's being... Didn't seem to be affected by the fact that we did this. Try to export this to the global scope, but or to the Windows scope. But be on the safe side, I'm gonna shut this one down, and I'm gonna also restart the web server. And we will do localhost 8080. That was pretty fast. Although it is still frozen. Oh, okay. Oh, maybe we are not getting this working. Like live television goes wrong. Okay, so I do think that it's sort of loading now. It says recording network activity, and it has do we have to recompile something? I don't think. We can just try a regular website. Yes, that works. Error in the console. Failed to load. Server responded. Yeah, that's just the favorite icon. Doesn't. I'm just really surprised that this is so slow. Let's remove this script module here altogether. Empty cache and hard reload. Let's do localhost 8080. So that was faster, right? Sorry about that. Let's remove this final part here again. So it should. Yes, now it loads fast again. Now it doesn't. That is strange. What is causing this behavior? It was the first time I clicked reload there, it just popped in, right? Let's do Firefox as well. Let's see if we have the same problem. My computer is really going, like I can sense that it takes this also. There we go. Reload network, so I'm gonna see, yeah, so reload. That's quick. Cache. Home. Back. Something here in the loading is not going very well. Something here is very slow, even though it's just 150 kilobytes and some other things. That is not good. I was not expecting that to be a problem, to be honest. Let's just try to do the init one more time here. That was fast, right? Now it's slow. Fast on the first go and slow on the second. That is really weird, especially since it happens in both browsers. Will be something about this server, could it? Let's try to get this. Let's try to get this working anyway, because I do really want to. I really do want to get this up and going. So we're gonna try to add this. We're gonna try to add the function to the window like this. It should probably only happen after init is done. So we will do it there. Can that happen? Or is that like a missing? I think maybe it will not be valid in that scope. Let's try this. If it takes this long to reload, then it's unusable, right? Did we get runsim? No, we didn't. Go down here. Save. Cache. Weird. So I tested some of this stuff earlier, and I did not get this this current problem with the reloading. So that is funky. Let us try to recompile this this thing. You can also now see if we did get the runsim. Like it's stuck there. It doesn't execute. Is it? Is it actually? Is it? Could it be that it is running the simulation in the background because we have it running? Because we have it in main. So I'm gonna try to recompile this. It could be that it automatically runs main, but I thought you had to specify that here. But I will remove that from main so that we are sure that we manually have to call it up. It could be that it just executes that file. Okay, so let's get away from here, and we're gonna do cargo build like we did before. And then we're gonna do the wasm-bindgen like that. And since we already have created our didn't we have our Python? Let's see, was it Python HTTP server? Is it? And now it's on 8,000. So let's just try and load it now and see if it's faster. So are we okay? So we do have an error message, but it's about the favorite icon, which we have not installed. Okay, so we did get this, and it seems the waterfall thing here says that this did go pretty fast, right? Talking milliseconds. Now we do have the run sim, or do we? Let's try run sim. So I actually think that it's running now, and the reason I think that is that it hasn't returned anything yet. It might be that it runs slower in the browser, and that we need to dial down the amount of people that are in the simulation. Let's see if it's using any resources right now. So yeah, it is. Chrome is definitely using resources. We have one CP here now. There, finished. So, believe it or not, we have actually successfully run our simulation. We've just been unaware that it was happening. Probably that is what takes the time when it loads as well, but I'm surprised at this. I'm gonna add one more thing to the loading file. I'm gonna add console. Console write line, is it? I keep forgetting. So we're gonna do JavaScript write to console. JavaScript write to console. Console log, that's the one. So console.log. Then loading wasm. Do we await this? Do we await this one? Do we have to do this? Can we do that from there? Not sure. Then we await that to finish before we continue execution. Unexpected use third word. It's not good. This. Done loading wasm. Run sim. And it goes. There you go. It's running. It's just not letting us know. Okay, so wouldn't it be nice if we could okay, so we know now that it is running, but it's just the black box thing. Like it's we don't know what it's doing. So the first thing we need is we need to put away so we can configure how many people are being simulated at any given time, and then we need to find a way to get the results out, right? So what I'm going to do is I'm going to create a button on the web page to run it, and then I'm going to create an input box where I can put how many people I want in the simulation. And then that's the very last step of this particular exercise. I want to have it. Yeah, we also have to. So right now the results will not be correct. The reason for that is that we are first not seeding people in the simulation. So we need to do that. We're not seeding infected people. So you need some people to get the infection going. So usually we planted 10 random people that have the disease at the beginning of the simulation. We're not doing that. So the simulation right now is just looping through arrays. It doesn't mutate anything in the actual simulation. And then we need to then we need to print the output. Okay, so I'm going to take a very, very brief break, just a couple of minutes, and then I will be back, and then we will get into making it configurable. We will initially just test and see how much time it makes, and then we'll make some communication back to the JavaScript that is calling it with the data, so we can print that data. That's, at least I hope we'll get that running. But that is also one of the things that wasm-bindgen should be able to resolve for us. Okay, so I'll be back in just a couple of minutes, so stay tuned if you're watching, and of course, as always, if anyone watching has any questions, feel free to ask them. I do check the chat, so also in the break, you can feel free to ask me any questions. Okay, I'll be back very briefly. Okay, friends, we are back with another part of the stream. Let's get straight to it. Okay, so we know that we have now successfully compiled our simulation, or our binary, basically our program, to WebAssembly. And the thing that we have to do next is we have to interact with it, we have to trigger it when we want in a user-friendly way. Let's go into the index file. We're going to create a button. So we'll simply say input. Actually, I think more recently you can just do button. And then you can say trigger or run sim. Trying to finish it with a or run simulation. And then we want the input. Type should be can do number, yeah. And we want to say people simulated, like that. We need to give these some IDs so we can fetch them out. The ID will be sim count and input. That's better, number input. And the ID of this will be run button. Like so. Let's look. Yeah. Looks fine, right? Now we can actually say how many people we are inputting, and we can also actually also add one that says how many days we want it to run. Let's do a break. We do the same thing, and this will be a bit dirty, but it will not be very pretty, and but it's just to test. Days simulated. Days input. Okay, so we have created an extremely minimalistic user interface with a stray clause. So we can now say how many people we want simulated and make it a little bit prettier. One simulation outbreak simulation sounds more sexy. And then we'll say people and days. And since we're at it, let's add a Google font. Use Quicksand, which is one of my favorites. Maybe not for web development. Isn't it very, very simple? We can just it had a thing here where you select the style, so we're gonna do medium. Good. Bad. Just add the style clause on the top. It can never be too stylish when you're making silly streams. Then we're just gonna, I think we're just gonna put body font. It's been so long since I wrote this. Font family is Quicksand. Can I just do that? There we go, and we have, well, didn't get that much prettier. Okay, anyway, we have we now have created that. So what we want to do is we want to be able to say, to have some inputs from these actually happen. So we should now be able to get these. So, okay, we're gonna create a function for ourselves. Okay, so we're now gonna create a function. We're gonna do a window run sim equals, and it's gonna be a function. Or can we just bind like this? I think we can just do that. So first thing we want to do is we want to run sim. But we want to do that, of course, when the person clicks something. So we want to get the elements. So we want to get n people input equals, so let n people input equals document.query selector. And we called it n input. And then we do the same for the two next ones, and days, and days input, and then it was run button. So we do a run button. Okay, you can just execute this and see if it fails. No, it doesn't. Yep. And now we should actually be able to, yeah, of course this doesn't run, so we can do run sim. venting. That's exactly the way we want it. And then we will now, actually, we will, instead of doing this, we will set up so that, okay, we'll catch these. And then we will take a run button dot on click. It's just called on click, isn't it? Equals. Then we can now do the thing we absolutely cannot do in Rust, although we're just now referencing things. Let's put an alert in here, or a console out, no, console log click, just to check that the button works. Try that. Yep, so the button clicks. So then we will say, so when it clicks, we'll just do starting simulation. Then we will run sim, and then we will say that we're done. Okay, fine. So in theory, we should now be able to click this and run the simulation, and we'll get a note when it's done. There you go. Okay, so we are now successfully telling it when to run. So now we have to now we have to be able to configure it. So what's interesting now is that now we can trigger it when we want, but how does the wasm-bindgen update our module when we are adding a parameter? Because that's what we got to do now. We got to add a parameter that says number of days and the number of people. You just let this run to its conclusion just to see that it prints done when it's actually done. We do see that it's spending a lot of resources. It's done. But the resources are, yeah, it did go down. I was just having it outside of the screen there. So then we know that it is indeed the road simulation that is running this thing. Okay, so let's configure the thing, and then we got to go back to CLine. We are in CLine. So it had excellent HTML support. I guess all these JetBrains products have this kind of, they have the similar IDEs for a lot of products, right? They just customize them for languages, but they share resources between them. Okay, so in our main here, we have bound this function, and now we need to configure it. So we have n people, and that's going to be a u32, unsigned integer, and then we will do n days, which will similarly also be a unsigned integer. And then we'll take n people and feed that into the simulation. And then we will take n days and set that as the final parameter of this. Well, it has to be casted to usize. Yeah, we can do that as usize. Cast should just work. Okay, so now we have configured this. So what is interesting now is that right now in our so in this JavaScript module that has this run sim exported function up here, it doesn't have any input parameter. So my question is, what happens to this when we now update the bindings? So we're going to pop out here into our command line again, and then we are going to build and export one more time. So I did briefly, I just did cargo build for target wasm unknown, and then I did the wasm-bindgen function, target web, output directory is the directory we put the stuff, and then I just give it the path to the binary that we generated with the cargo build. Okay, so let's have a look, see now. Do we have, and here it is. Look at that. So it has updated. It has updated the bindings. It does what it says on the box. It actually works. Okay, so now it has configured this for us. Oh, that's a bit of magic, isn't it? Little bit of magic, I have to confess it is. So we changed the function, and then wasm-bindgen changed the JavaScript for us. And I think more importantly, it feels like sort of, okay, you can understand what it does. There's no magic trick here. It just you can see exactly what this thing does. It's also interesting that this this thing that you get here from instantiate from WebAssembly contains this imports, and isn't that the one that we? So and then it says that, because we were looking at this earlier, we said imports and module, and where does exports come in? Because we were looking at this object here. Somehow the WebAssembly itself seems to export this wasm run sim thing, right? So perhaps we could just use this directly. Although it is very convenient to have this initialization function just provided for us by wasm-bindgen. Right? Okay, so now we will need to update our index file again because we need these values. So we will take the values of, when we click the button, we'll collect these values. So now we have our, we will bind, so let n people equals n people output, is it value? People input, is it, I think it's value. Isn't it like when you get like a value in JavaScript from it's a property from input? I think it's called value. Then it's let n days equals n days. Actually, I call this input. The reason is I want to separate the control from the from the value that it has. So we're actually just going to add the n people here plus comma days, and then it will be plus n days like this, and then we will do that, and hopefully it should now tell us that it has successfully collected these. This is interesting to know what happens when it crashes, right? Because we don't need to regenerate this now. The only thing we need to do is reload this in the browser. Okay, so people will be 5,000 and days will be 20. Then it will be a quick run. That was very fast. If you created 500,000 people for 200 days, 100,000 people for 200 days. Oh, okay, that did not really succeed, did it? Because it was way too fast for that to happen. Yeah, okay, interesting. You're calling the function without sufficient variables, but we're not getting an error message. That is not good. Because it's obviously not running the simulation. I did not like that, to be honest. Okay, we can try to insert here the n people and n days. That was a bit on the edge. I wish that hadn't happened, because it sort of felt sort of sturdy and strong until this point where it's not telling you that it's failing. So we'll do 500,000 people for 300 days, run simulation. Okay, so now it does run. Yeah, so the core is being utilized, so it is indeed simulating simulating this 500,000 people. But I really disapprove that it doesn't tell you that it went wrong. There might be a way to catch errors, though. I certainly hope so, because it's not nice that it failed at that. Okay, but we do now have a way to run our simulation in the browser. So the next question is, do we probably want to capture the output and actually see that it works. So the final thing that I think I will have time to do today, because it is getting a bit late for me, is we will try to transmit some data back, and then we have to see people in the simulation. So we have to do those two things. We can start with the transfer back of individuals, and then we can report the final number, and if we get that working, we'll see if we have time also to do the plotting so that we can get data out there. Okay, so what actually comes out of the simulation is, of course, a list of, or if it's done the way I did it at the end of the more complex simulations we wrote, it gives you a list of numbers that represents how many people are recovered, how many people are infected, how many people are susceptible at any given day. So in the simulation, so it will be a list equal in length to the number of people, to the number of days you ran the simulation. We will do that. It's still going, and it is still going because we have 500,000 people here, so it is quite large. So we will, but we can go back. And what we need to do now is we can leave the index file and the HTML for now, and then we have to go back. We have to collect the data in our simulation. The first thing we have to do is in simulation here, we have to seed a certain number of people that we want to get the infections going. So when we create a new simulation, I'm now going to add a new parameter here in Rust called nseed, or seed number. It will be a u32. Oh, sorry, I'm actually in the wrong place. The other thing we have to do is we have to actually reestablish randomness, because right now we are not, we're using this, we hard-coded this get random here. So what we have to do is we have to import what's called the OS random number generator. And that's a little bit different from just calling random like we've done before. In fact, we can try to change that so it calls random from the rand crate, and then we'll see the error that we get there. Because the error itself is interesting. It will tell you where the problem is, but it's also very hard to interpret what the problem is, right? Okay, so we got this running. Fine, let's do one thing at a time. The first thing we can do is actually, first of all things that we do is we can add some default parameters to these buttons. So in people, I guess we don't have a field called value. So we will say that the default number of people is 10,000, and because we're testing, and the default number of days is 100. Then we make it a bit simpler to test the simulation. This should run relatively quickly, yeah, but this should still generate numbers and infections once it works. Next thing we want to do is in simulation we need to catch, as the simulation progresses, we need to catch the number of people that are sick, susceptible, and so on. We're actually just going to add that to our simulation for now. This is not how we did it before, because we were a little bit more elegant. But right now we want to say, self count, and that is a vector of u32. And actually we're just going to count susceptible and infection. Oh, we can actually count recovered and infected. When we are creating a simulation, then we need to add these missing fields. So we're just going to create empty vectors like this. Thank you for that, C line. You just saved me a bit of time. Okay. So as we are going through the next day, we are going to now deal with this to do. So we're going to say self dot, and then we were rec count push. I'm going to push rec. And self dot inf count push inf. Just going to do these two now. Log results. That means that for every time we take a day, we get a new sort of element in these lists, and we can read those out afterwards and look at the dynamics of our outbreak. Next thing, okay, so we can just see that this runs. Yes. So we know that this compiles and works. The next thing we need to do is we need to seed people in the simulation when we create it. So what we are actually going to do is we're going to take this, we have this function called infect. So what we need to do now is we need to, for as many people as we want, and we will seed, we'll seed 10 people all the time. Let's, so let's sim equals simulation, and then we will work our way through the simulation. We'll return sim at the end, and then we'll seed sick individuals. So for 0 to 10, and we're just going to hard code this for now. We're not going to keep that number. We're going to let idx equals self.pick. No, not self. Sim.pick random index. And then we're going to do sim.infect idx. Yeah, so we need to have sim be mutable. Does this run? Runs just fine. Because now we know that we are seeding people, so we are randomly infecting 10 people at the beginning. That means that on the first day there should be at least 10 infected people. We can actually test that, but we have taken... So we can say that main here runs the simulation, but it runs it for 100 people, no, 10,000 people for 100 days. The problem was, of course, that this, when we loaded it, we didn't want anything in main here because main seemed to run anyway when we loaded it. I think that's why we had the load problems. We don't want the simulation to run every time. So I think we're just going to trust this for now. But okay, so we can just now check that all this runs so we don't get any nasty surprises. So we will compile and we will run the binding generator one more time, and then we will reload and run. And it runs. So I think in principle now all of this should be working fine. I think that the last thing that we need random generation. So we need to include again our rand crate. Right now there is no actual random pick, so the seeding always picks the same person. And that is not good, obviously. So we will use rand, but the thing is that it's actually not quite as simple anymore. We can just try now to re-establish. Usually, before we used the crate call rand, we can still use rand, but we have to configure it a little bit differently. And this was something that took me a little while to figure out. So we will now use. So we'll use extern crate rand, and let's just now see if this compiles. It does. And what we used to do before, if you go to the simulation, and then we have now a function called getRandom f32. So we'll replace just this hard-coded number with that. So we're going to do, before we would just do random. The reason we wanted to do that is because we are importing that from this crate, so this should just run. So if we load this, this in my initial testing, so now we're recompiling it for the web browser, for WASM, and at least when I did it initially, we had a crash. There we go. So what is interesting here is we have to look at this message. So the only thing we added, the only thing we changed was that we started depending on the rand crate. There's nothing wrong with depending on an external crate. But it seems like it has a problem getting these. It has some problem here generating this this random number. I'm not exactly sure what it is. It does. It looks for a random number generator on the current thread. Problem is that that is not something that runs. We don't have a thread. I think maybe that is the reason why it fails. So without telling us, this actually doesn't work. I'm also curious to see how big the wasm file was now. Yeah, so now it went up to 346 kilobytes by including the rand package, which of course has its own dependencies. And it did compile, so I'm going to assume that this additional 200 kilobytes that were added here comes from that package. But there's another, so here's the thing, and this is the thing that took me a little while to figure out. There's more than one way to call in a dependency, and you can, so right now we're just putting dependencies in rand. But apparently what you can do is also you can add dependencies.rand, and when you do that, actually it did offer me some thing there, and then you can more specifically ask for things about this package. If you do this, this should compile and it should do the same thing. And now it hasn't fixed any of our problems, but now you also have features list. And if I remember correctly, you have to specify it like this. Then yeah, so now it recompiles. I don't think it's enough to do that. I think we have to use another random number generator. But we're just going to give it a try, because if it works, we're lucky. Oh, it actually ran. Okay, so that means that the package is smarter than I thought. Yeah. The thing that I'm missing here is that it took me a little while because I actually switched to another random number generator, but it seems like maybe the package does that on its own when you enable the wasm-bindgen feature. But it seems like sometimes you have to change the features that are compiled in the packages that you choose. So that's something to keep in mind, and then the syntax is different for that. How big is it? 363 kilobytes. So it is roughly the same as it was before. And it runs. Beautiful. Okay, so that's cool. Now, but you still don't know if your simulation is actually working. We don't know that, so we gotta get some numbers out of it. Actually, the thing that I want to do is I want to export to JavaScript the results directly. So now let's see if we can wasm-bindgen that one. The simplest thing we can do is just to export a number. So if you have a look in our REST function in simulation again, what we in main we could now at the very end here, we can just try this first. We can just you can pick out the final day. So when we're done with this, we can report sim.recovered rec count. Did we have a last? Yeah, we did last. Nope. The last one is yeah. How do we take that one out? Actually, maybe we do get. How do we, from a collection like this, how do we get the final one? I think we can just do last.clone. Yeah, so we can do last and wrap clone. Okay, so in principle now we should get so I'm just going to turn off one thing. I'm not sure if you see it on the stream, but we have a thing called nightlight in Windows, which gives you sort of a blue light filter, but that's not what we want, right? It's actually really pleasant, but right now for a stream, in case it shows up on the stream, we're not going to have it. Let's just see if this now... Okay, so let's first look at the JavaScript. So still we have... Oh, did it change that much? No. And maybe these things were already here. But so okay, so right now this run sim function doesn't return anything. It just takes these inputs, and we got that for free when we updated the bindings. So let's compile and update bindings one more time. We're gonna build and do wasm-bindgen one more time. So now indeed it returns. Okay, so I guess does this mean that it returns this or 0? It's a triple arrow operator in JavaScript. I don't know that operator. Let's have a look. Triple. Okay, so it's digital operator. JavaScript. This one, right? Without sign, right shift without sign. Okay, so it shifts the value for us. So this is because it's unsigned, I guess, that it has to do this. Interesting. That's good that you thought about that, right? Okay, let's run it. In principle now we should be able to see on the final day how many people are... Yeah, we're not collecting it. So we need now to see how many people are recovered on the final day. We're going to just add that into our... it was an index HTML. We had it, and we created our function. So we will catch that final rec equals, and in the beginning this is 0, right? Console done. Recovered on final day. Plus, and then we're going to do final rec. Let's try it one more time. See if we get the output. Lovely. It really works. Look at that. So we put 10,000 people in, and recover on the final day is 9,437. That means, so roughly 5% in our sim usually goes without infection. So Try it one more time. We should get the similar but not the same number. We do it one more time. We should get similar but not the same number. Right. So there's a stochastic element here. Works. It really works. We see that bindgen really it works for us, right? Neat. The next thing we want to do now is slightly more complicated. We want to catch the entire output. So the way we'll do this is we will actually in our simulation we will create an entirely new struct and try to export the whole shebang. Public struct sim result. And the sim result actually is just going to hold this. Because of that, we will take, we'll create a public result. Actually, we will, yeah, will we do that? Yeah, that will be a sim result. Like so. Now we got to change that here because now we are no longer, yeah, so result. This is the initializer for the simulation, so that will now produce a sim result. And then we need cline. And then when we update the days, we no longer directly push onto our ourselves. We push onto our result like that, and it should now work. No field rec count on type sim. Okay, where are we breaking? We're breaking in main. That's fine. So we are doing. So we can actually do result here, and it should work now. Nice. Okay, now comes the thing. So what we want to do now is we want to make sure we can actually export the sim result. So we will add wasm-bindgen prelude up here. Use wasm-bindgen prelude, which means we import the fundamental things, and then we will take the sim result and see if we can do bang wasm-bindgen. Is that correct? We did it in main, right? We did. Yeah. Okay, can we export a struct like this? No. The trait bound. Okay, so maybe it's not that easy. Copy is not satisfied. Okay. Does this mean that only copy types can be exported? I think we can just add copy type. However, the sim result. Problem is if we do that. Okay, so now we need to think a little bit. If we do that here, the problem is that we will maybe mess up in passing this object around. Will we not? Maybe not. Maybe not. So you can simply add frequently. You can just add copy trait to these things. Is it? I don't remember the syntax. Is it just copy? I don't think it is. So we'll just go rust add copy trait. Rust add copy trait. Yeah, so it's derive, and this I think this is the easy way to do it, and you don't need to automatically implement that. You don't need to implement the method. Okay, macro must be placed before derive. Okay. With copy may not be implemented for this type. Maybe we cannot so easily actually implement this on here, but we can try something. Okay, so this does add a bit of complexity. It does mean that you have to. I know that there are like JavaScript values and stuff in wasm-bindgen, so there are probably ways we can do this. One thing I think I will do is I will actually think of the simulation more as a separate entity that doesn't have to worry about WASM and WebAssembly. So instead, I will create a structure here with the results. So I'll do public struct sim result here, and I will put the final rec, which is u32, and final inf, which is also a u32. Then I will take the values out of the sim here, because in this one I do want to provide as wasm-bindgen. Like, I just did this with this compile. Cannot find sim result in this. Yeah, of course, because I did change that in here. So what did we do? We took oh no, I messed it up, didn't I? So we had public rec count. That was a vector of u32, and then we had pub inf count, which was a vector of u32 as well. And then instead of sim result here, we would create the missing fields. Let's have CLion do its magic. Thank you. And then we will go down to the update function again, and we will take the result part away from here. Count. Maybe I put the wrong. Oh, I did put a capital C. I think we can refactor that. Count. See if it compiles now. Result. Yep. So we are currently in main. We are trying to pick out result, which we will not do. Okay, so now it compiles, and we do have this sim result. So what I do want now is I want for main to produce the sim result, and I'm very, very curious to see what this will look like in the JavaScript. So we'll create a sim result as the final thing we do. Okay, so it just contains 0 for now, and then okay, so now this should also compile. It does, and then we will recompile with cargo build, and we'll do wasm-bindgen to generate the bindings. Do rapid functions, and now I just want to first have a look and see what we are returning now. Okay, so now we have our function run sim. And it returns an object this time, or it does this thing called sim result wrap this value. So it takes whatever comes out here and it wraps it, and it does create something called sim result. So that is, can we look at that and see what it is? It has a wrap and free. Raise it from some prototype here. I don't know where that is. So I'm gonna pass on inspecting that further. But it is curious to see now when we look in the sorry about that. We go into index. What do we get as the final result? And I am tempted to log. We're gonna console log, and we're gonna log this final rec. Can I take anything out of this? No. But I want to see what that looks like when we do run it in the browser. Okay, so let's run it again. We'll run the simulation and see what we get out here. So we get a sim result. It just says pointer. Ah, is that because I guess we cannot do yeah. I wonder if am I exporting the right thing? This doesn't actually have the values that we put there, right? Let's have a look in the main again. So we are reporting the sim result here. If I ran this, we can see what it would look like in the debugger. Run. run sim, and we will run 10,000 or for 100 days like we did otherwise. Good. We're going to put a debugger. The breakpoint here, and let's go. We didn't catch it, of course, so we can catch it. So we do let the result equals this. And now we can inspect the result in the debugger. So the result is, yeah, so the result does have values, yeah. But not the thing that we exported from wasm-bindgen. Let's see. I don't think that there is another I don't think we can get those as a final rec. We can just try to catch that object, but I don't think that we can just get that. I don't think we can get those values out of that object that the JavaScript presented us right now. So we will actually set the window.final output equals final rec, and let's check that compiles. We will cargo build for WebAssembly, and we will one more time. We should put up a build script for this if we wanted this to run. And cargo supports build scripts. Okay, so let us one more time run it in the browser, and this time we should be able to inspect that object. Now we have final output, and then can we do rec? Final rec is what it was called. Count. So actually we cannot collect the values from this one. Let's have a look one more time at wasm-bindgen. Ordered rest types. It may be that because of everything here called supported types. Yeah, so example Rust usage, and here it says, oh, I think I know the culprit. We didn't put public in front of these. Could it be that simple? Because we don't see that problem since we are in the same module. I think actually what the problem is the public, the missing public statement. Add that to recompile, and let's see now. Okay, so we can actually now see the final results. What I want in there now is a vector of numbers. Is that possible? We did have a problem with that before, but we can add a public rec recovered, and that will be a vector of u32. This caused us problems before. Right now is we can just create a 1, 2, 3, 9, 9. So this will give, actually, yeah, of course, commands there. Doing too much MATLAB. Let's build. And no, the trait copy is not satisfied. So it means it might not be possible for us to export the vectors, or let's have a look on that page with supported types again. can actually do wasm-bindgen vector. Yeah, they do actually have an interesting point here. We do have the serialize function, so we could, even if you have trouble with the direct bindings, we could output the results as through serialization. Because there's this really excellent, like really excellent serialization tool called SERD in Rust, and we could probably do that. But anyway, we are actually running out of time for this stream, so I think we will not be able to, like I predicted, to finish this today. We will remove this and just get the final 2 results out. They are proof that our the final rec is. So the things that we are outputting here is actually proof that the simulation runs in our browser. So it is that is neat, but there are some hoops you have to jump through for this to work. Let's just compile this, see that it runs, and then we will catch these 2 things at the end of our at the output when you run it in the browser. So let's do that, and let's run it again. Infected on the final day is 6, and 9,399 people recovered. Roughly a little bit over 5% in this run remained remained without any infection, and we did get 6 people infected on the final day. I think if you ran it for 150 days, there would be no infected left. And we are approaching this thing. So if you cut it halfway, so we cut it at 60, we would have a much higher number of infected. Now we do see that the simulation runs. Okay, so quick recap. I think that's towards the end of what I have time for today. I did really want to make like beautiful plots with this, but I think maybe I will move on to other things. From this, it would be cool to do something like Plotly to like reproduce these graphs that we have previously made here in LibreOffice with the data that came out of the sim. But still, I think all things considered, it is pretty cool what we have achieved with relatively simple means here. We have taken a relatively complex program written in no, it's not complex. We have taken a program written in Rust, and we are now running it in our web browser, and it seems to be running rather fast. But some concerns were that functions fail at one point without telling us. That is not good. So it seems like the boundary between your WebAssembly and your JavaScript might be a point where you need to think a little bit. It might also be that wasm-bindgen produces a lot of things that I haven't seen yet, because I haven't, to be honest, I haven't read the book about it. I just scratched a little bit on the surface of this. But if you think about what we have achieved here, we have taken that Rust program and basically just put it in the browser. We had to do a little something in the rand crate because we couldn't use the only thing we had to do with the rand crate was to tell it to compile with wasm-bindgen support, which means that it uses the JavaScript random number generator for this. So but with that minor modification, literally just 2 command line commands generates for us the JavaScript and TypeScript bindings that we need and the code to load that WebAssembly. So it is pretty sexy, all things considered. And I think I'm not going to do that now because I think I know that it works. But you could see just a moment ago that I could compile this binary also to run it on my Linux computer here, right? So it doesn't stop me from the fact that it has now that I can run it in the browser did nothing to prevent me from running it on Linux. So, and it's the same code, it didn't need any adaptation. And Cargo has support for something called workspaces, where you can put this into a library and compile it to multiple binaries and multiple command line tools. So again, Cargo also looks really cool. Yeah, I think I'm gonna end the stream there. 2 hours and 9 minutes is 2 hours and 14 minutes is more than enough for now. So thank you to anyone watching. If you missed something here, it will be available on Twitch for a while, and then I'll also put all these things over on YouTube for Knusti TV there. The next thing that I plan to do is look into event-driven programming in Rust and alternatives to this particular pattern. This exercise that we did now has mainly been to learn the Rust syntax and how to deal with the memory management, and I feel like I'm getting a little bit of a hang of this, so it's time to try something more advanced. And the more advanced thing is definitely this pattern of event-driven programming, and it's interesting to think how you would, because if you're programming for Windows, for instance, you tend to do this. Or if you make graphical user interface programs for Windows, you will do this event-driven programming where you will set up your controls, and then you'll secede control to the event loop, and then whenever something happens that trigger an event, you will mutate the state of your system, of that tree of controls and the control states. But that's not so easy in Rust because of the limitations of the borrow checker, and maybe for good reasons. So I read an article where they described how you could do these component-based systems more similar to what you do in Unity 3D if you ever programmed in that. And I did like that when I programmed in Unity, and I can really see how maybe you do want it, or how you could structure something like event-driven programming in that way. And then using that pattern, you might actually get more advanced graphical user interface programs. So you can, it means that, for instance, let's say you wanted to add accessibility to your user interface later, you would perhaps be able to just add that as a component to this tree of data that you had created that represented your user interface. So rather than changing the objects in this tree, you would add components to the already existing objects. And this is neat. I think this is a cool idea. So I do want to try that. I think that's it for the next stream. In the previous 7 streams now, we made our little outbreak simulation, and we have successfully made it multi-threaded, and we have successfully run it in the web browser, although the multi-threaded one could not run in the web browser. But yeah, I am enjoying my Rust experience. I have to say that the learning curve is definitely present, but it feels like progress in this particular domain. So far I really like Rust. I've been enjoying this, and yeah. Okay, so thank you to anyone watching. Please subscribe if you like my channel, and I'll be back maybe as early as tomorrow, but then I think actually tomorrow it will be some VR gaming, and I'll do some Echo VR matches again. Okay, bye for now.